So now both, so there are two types of paths that we call it here. Okay. So if you look at, you have something called, so Q2SI, Q2SI, which is known as scan path. Okay. And the Q2D, that is known as functional paths. Q2D is known as functional path. Now remember, your, so you had seen yesterday, I mean, the last class, we used to design, say, some kind of OR gate, say, AND gate, say something like this. Okay. Now these are all your regular combinational logic, which is comes under the func path. Okay. Now the same Q would go here without any kind of combinational logic to Si. Okay, so this is your D and this is your Si. Okay, now this particular thing configuration, right? If you look at this Q2SI, right? Q2SI paths are always going to be just shift registers. Okay, it is same function when it works as a shift registers. Now, what is the use of this shift registers, or what is the use of this Q2SI paths? Okay, now if you look at, say, this Q2SI, okay, now this Q2SI and this Q2SI. So they all kind of one after other, they keep, it's kind of, serially connected, the registers. Okay. Now, what is the use of this, you having the scan path and how it is going to be used? So now if you look at, ideally, say this is your D and say this is your SI. Now you wanted to test a chip or the circuit. Okay, what we will do is, okay, before that, let me explain what is the meaning of SDFF. So this is your DFF. Okay, now, so you will have a mux. Okay, this is going here, and this is your CLK. Okay, so this is going to be your regular D, and say this is going to be your SI, and this is going to be something called scan enable. Okay, now what is this meaning? When I say scan enable is 0, okay, it means it is operating in func, it is trying to capture the D input. Okay, that is called functional. Now if you give 1 here, what is this meaning? It is in test mode, you are under testing. So basically, any kind of chip that you work on, immediately after your manufacturing, you need to test. Okay, so at that time of testing, how would you test? You just make this as a 1. Okay, scan enable equal to 1. That means you are trying to tell the design that you are under testing now. So the moment you make scan enable 1, so you are telling the system, or probably, you're triggering the circuit, which would be, you know working in the, working like kind of, the test mode. Now So any question on basic this SDFF before I go and explain you this, so that you understand why I'm stressing on the SIP registers and you should learn about it. So this is your regular DFF, okay? Now converting it into scannable D flip-flop. So this is the kind of circuit that SDFF is going to have. If you look at, so this is your SDFF. So now you can equate, say D pin is there, SI pin is there, SE pin is there, clock, as usual reset Q and all of that. Any question, any doubt? Yeah, go ahead. Meaning what? I'm not getting. Yeah, right. So this kind of, you mean you're talking about this picture, the top picture. So as I told you, the scannable path, basically the scan path will not have any combo logic. I mean, it will have a buffers and an inverters, but other than that, we usually don't keep any kind of logic in the scan path. It would be just Q to SI, Q to SI, Q to SI paths. But if you look at this Q to D path, you will have a lot of gates coming in. This is how it would be designed. No, no, that's what I'm saying. Logic gate meaning there will not be any kind of operations that would be performed in this path. I'll explain you why. I just wanted to make sure you guys understand what is the meaning of SDFF so that it would be, easy for you to understand why I am telling this. So scan input 0. Okay. Now this is scan output 0. Okay. Now, so what we do is if we wanted to test the whole system. Now remember one thing, whatever that we prepare, okay, so whatever the circuits, right, you are going to work on, right, so all of them in the end they all would be converted like this. So it's a kind of something called a layout which we would be seeing in probably not today's class and maybe next week. So now imagine all these circuits are manufactured in really lower nodes. Okay, a simple hair fall, okay, a simple hair, whatever, everyone has it, no, everyone knows a simple hair, one hair can spoil multiple ICs. Now if you look at, if there is any kind of, now imagine, say this is kind of VDD, okay, now this is kind of signal. Now if there is extra metal piece gets dropped, now what will happen? If these two become short, what will happen? So basically if you look at, there is a Z pin. So say this is your NAND gate, assume. Now the internal structure is something like this. Now say extra metal piece or slight variation at the time of manufacturing, what can happen is this might get shorted with your VDD. Okay. Now if an output gets shorted with VDD or anything, say for example if your input, or it can be anything, Okay, so these this circuit will not work as per the expectation. Okay, there is, you have designed a circuit well, but due to the manufacturing issue, there is some issue, some, the chip might fail. Okay, now to identify, so these are all some things unexpected, the shorts are probably, the issues. So this is something that we call it stuck at fault, stuck at 1, stuck at 0. So imagine if that is stuck, it gets shorted with VDD. That means it is kind of stuck at 1. That means this particular node or probably this output, irrespective of the input, always gives 1 as output. Now, to find out if there is any kind of stuck at faults in the design, okay, we use this registers. Now imagine you just give 0 here, 0, 1, 0, 1, something like this kind of pattern. Now you keep giving enable, scan enable equal to 1. Okay, scan enable equal to 1. So basically you are giving scan input. Okay, this is your known vector. So how shift register, you load the data and shift it, right? The same thing we are doing here. Now you just enable the scan. Now that means whatever that you are having it in scan input will be just passed here, one after other, one after other, one after other. Now say 1, 2, 3, 4, 5 pulse. So after 5 pulse, you start getting first input. Now remaining 5 pulse, if you are getting the whole output, the output, if it is same as what you have given, okay, that means you are stuck at free. That means you are stuck at free. Now imagine throughout this, say this flip flop Q is kind of, stuck at 0 always. Now what would be your value here? Throughout this node, if there is anything that gets stuck at 0, so you will see only 0, 0, 0. So now this way, with the help of shift registers, we will be able to figure out if the chip is kind of, free from manufacturing faults. Remember, the stuck at is something that people also call manufacturing faults. Manufacturing fault. Okay, so that is the reason, these are all something that even I use regularly on day-to-day basis. The shift registers and this Q2 SI paths and all of that we keep checking, every day. I mean, every day meaning before tape out or any experiments that you do, we always look at both Q2D and Q2SI, and always remember Q2D is going to be critical as that is the real functionality, but whereas Q2SI is something going to be less critical. The reason is when you're testing, you will always go with 100 megahertz clock period. So all your testing or say test clock, okay, test clock would be always with 100 megahertz, but your functional clock would be always frequencies like kind of 500 megahertz or 1 gig and etc. Okay, so this is something that you might have not heard in the school, in your college days. Functional frequency is going to be say kind of 500 megahertz or 1 gig or more than that. Okay, now, but remember your whole testing frequency would be 100 megahertz. Okay, so your Q2SI path is basically a shift register, serial in, serial out shift register. So any question here? Okay. Now for this testing purpose, what you are adding extra circuit. Now you, if you are trying to keep more frequency, you would end up in optimizing your circuit little more on the test paths and etc. So the tool would actually, add lot more cells on the paths. I mean, basically the buffers and inverters for taking care of transition. Okay, probably you won't understand at this point of time. You will understand when I get into something called STA and power analysis. So remember, your power, overall power consumption, alpha CV squared F. So that is going to be today's topic. Okay. So if you have a frequency which is on higher side, you will have your test power going up, and also your, see, there are multiple reasons. And moreover, if you are keeping higher frequency, your test cost also going to be higher. Yeah. Okay. Maybe you guys, for it's for everyone, right? You can note it down. Why we keep test frequency as 100 megahertz? Why not 500 megahertz? You guys go and explore. You would, something you will learn, right? Yeah. So now, do you guys understand the use of the shift register where we use in industry? Any questions? I'll give you a minute to ask questions, if any. Okay. If anyone want to explore, okay. So what and all we discussed now, I'll just give you a quick, heading kind of thing. You guys can go and take, you can read it later. So we talked about basics of DFF and SDFF. Okay. So what is the difference between SDFF and DFF? Basically, okay. So we talked about DFF and we also talked about SDFF. Okay. We talked about something called scan enable. Okay. And we talked about something called stuck at fault, stuck at 1 and stuck at 0. Okay. So this particular thing. And uh, we also talked about something called manufacturing fault. Okay. Now, if you look at, these are all, the whole lot of things comes under the DFT side. Okay, these are all DFT concepts. There are many other things. So basically, say for example, I talked about, stuck at falls, right? Now, what if your transition, so 0 to 1 transition, right? If this transition is, it's something like this, it's kind of always very, the longer transition. So there is something to figure out this kind of faults and etc. So if anyone wanted to learn on this side, okay, so those are all things comes under the DFT portion, which you can go and read it. See, people call it fault modeling. It's called fault modeling. Okay. Okay, I think moving on, since there are no questions. Remember, okay, we also talked about Q2D paths and Q2SI paths. What is the meaning of Q2D and what is the meaning of Q2SI? We talked about test clock frequencies and what would be your functional clock frequencies. Okay. Okay. Moving on to- so we also have talked about the counters. Okay. We also have implemented a counter last week. Okay. So This FSM will just quickly go over, but I will not be spending too much of time because it's not at all needed for PD engineer. Okay, these are all something that front end guys would be, needing it, not the back end guys. If anyone hating the FSM concept, or if you are not in a position to, or if you don't want to do this, then front end is not for you. Okay. Okay. All right. Um, So it's basically the design. So we have talked about registers and then counters and all of that. Now the advanced version of the design skill is going to be something called finite state machine. So what does this meaning? Say for example, uh, you have some kind of sequence that you want to follow up when you're in based on your input. Okay. Now we always you go for something called finite state machine. Okay. Say for example a simple thing, if you ask me, there are a lot of real world examples, but since I'm not from the design background, I may not be able to give you much. But say for example, one is kind of you wanted to detect this sequence. Okay. Or say anything like that. Say for example, you wanted your input. Okay, this is your input, and if this sequence comes, you wanted to give one output. Okay. Or if there are two things, one is, can they overlap, can they not overlap? So there are a lot of design styles or probably design requirements that we need to consider. But as I told, FSM, we will not be spending too much of time on it, just to make sure PD guys, to be honest, even I have not done any FSM in my whole career. So the way I explained your shift registers and counters and all, because I know I've been working on those kind of designs and etc. But this FSM is something that would be, would not, we don't need that for the 3D engineers. We won't be using anywhere. Okay, all right. Now moving on. So a state machine is a digital device that traverses through a predetermined sequence of states in orderly fashion. Now, what does this mean? So it's basically traverses through a predetermined sequence of states. So that means, say for example, you have this, you're starting, say with state A. Okay. Now state A to state B, state A to state C, and it's kind of, so you have a states, and based on your input, say if it is 0 and 1, so it would either go here or stay in the same state and etc. So there's something that we call it orderly fashion. So you design, or you tell, or probably you design a circuit that if it is kind of 1 1 1 or 0 0 0, so you go to all the, say state E. Okay, something like that. Now a state is a set of values measured at different parts of the circuit. Now, there are two types of state machines that commonly used or commonly available. One is basically Moore machine. Okay. Second is Mealy machine. Okay. Now, without getting into too much of it, let's just try to understand. Now, say this is your counter. Okay. So this is your counter. Okay. Now, say it is at zero state. Now, say you get a pulse. Now, what is it you do? You count it, you move to the next state. Now, you get one more pulse here. Now, the input gets one more pulse. Now, you move to another one. So, now, if you're going through all this, now, end of it, you reach to the origin state and you reset your output to, so basically, your output becomes, say, for example, kind of 1, and you reach to your first thing. So, there are different styles of you implementing this. That's what we will just, take a look at it quickly. So, how the design has to move from one state to another state. That is what something that we call it FSM design. Okay. Okay. Mealy state machine. What is this meaning? Mealy state machine meaning output depends on both present inputs and present states. Okay, it's simple, right? If you look at A is your state, B is another state, and C is another state. Now remember, it actually depends on both present inputs and as well as your present state of yours, the your whatever the state that you are having it. Okay, now say for example in this case, let's quickly understand what is the meaning of 101 sequence directive. Okay, say for example you have a kind of, say, A, B, and then say C. Now this is your input. Okay, now you moving here, what is this meaning? It is going to be kind of, say, 1, that's your input, and your output is considered as a 0. Now say C, this is going to be 0 bar 0, 1, 0, and 1. Now it has to be reset to A. So that means 1 bar 1. Okay. Now when I say this, that means if your input is exactly 101, first time from A it will go to B, from B it will go to C, and from C it will go to A. So that means this sequence is kind of, detected. Now you need to understand. Now let's say if it is 0, so you have to roll in here. So 0 bar 0. Okay, and here if it is 1, so 0 1. Now say, what if you get one more? So what is that you wanted to do here? You wanted to continue, or it is not our sequence, no? 0 1, basically 1 1 is not our sequence. So basically you need to go back to, so this one. Okay, 1 bar 0. Okay, and so any state you will have two inputs. Basically the state 0, what is the what the where it has to go in case of 0, and where the signal or probably the state should change when in case of 1. Okay, so when you are designing this kind of states, okay, the sequence, the FSM, you need to make sure always both ones and zeros are considered. Okay, now in this case, so we have done this 1 bar 1. Now what if it is 0? So 0, assume it's kind of 1 0. Now 0 meaning what? It is going to be kind of, supposed to go to A and 0. So you have to design it in a different way, but this, you, whether you want it to overlap. Okay, now if you ask me, when you are implementing, you see kind of, things that you need to change, right? Say for example, now in this case, overlapping. Say for example, this is going to be, say, 0, meaning it is, the output is going to be 0. Now if it is a 1, you go to B, saying 1 bar 1. So that is your actual state. So this FSM is something that if you understand it very well, then it is going to be easy. Otherwise it is going to be kind of, little tough. But ideally, if you ask me, do you really need all this knowledge for getting into PD or working in PD? Absolutely zero. The circuit, so the circuit, right, if end of the day you design this kind of FSM, then what is it you do? As usual, present state. Okay, and then your inputs. Okay, and your next state, and then outputs. So you will actually, design your implement your design something like this, and then as usual, K map. Okay, and then gate level circuit. So that is a kind of design process people follow when it comes to state machines. Okay, so mealy state machine meaning the output depends on both input and as well as present state. Now if you look at here, the state will not, when the moment you go to state, there will not be any kind of output. So when the transition happens, then only you'll see output. Okay, then only you'll see an output. So this is something we call it Mealy machine. And and I'm not asked going to answer anything for this topic, because I'm just trying to give you a brief idea. Even if you're not understanding, that is still okay. Move. Okay. Now remember this: the output states depends only on the present states. There is nothing else. Now if you look at previously, melee meaning, and the input happens, right, changes, so it is going to be kind of 1 or 0. Whereas in case of move, each state, the moment it goes to the state, you will have the output. Say A bar 0, that's kind of output. B. So each state has a kind of its own output. So that means it depends only on the present state. There is nothing else. Okay. So this is the kind of style that called as a Moore state machine. Okay. So with this, officially the first chapter is over. So any questions? Um, I'll give you a minute. Meantime, what I will do is I'll try to bring up a design and show you guys, so that you guys get an idea. Okay. I'm just opening the design in the tool. Okay. Bear with me for a minute. So you will get access to the tools and everything. Okay. And you will also be able to explore the way I'm showing you here. Okay. So any design that, right? So you will have, these are all something like kind of, macros. It's called memories. So you guys might have heard about like memories, like two types, right? Read only memories and random access memory. So ROM and then RAM. So we use mainly the SRAMs in the design to store the data when the system is doing computations or operations. Okay, so we use a lot of macros, or say it's called memories, mainly the SRAMs. Okay, so if you wanted to learn on that, so let me just give you a quick thing. So SRAMs, that is what you would be using pretty much in our designs. I mean, every design you will have that. Now there is something called a single port. Okay, and there is something called a dual port. You might want to go back and read it, so you will get some idea what is and how they are different and etc. Okay, so this you can take it as a homework, also as a part of assignment. Just explore and write it and submit it. Okay, now, so you will have a different types of macros itself, so different size. Say for example, this macro, if you look at 64 bar 8, so if you look at here down, you will see some kind of display the information would be displayed. You see here SRAM, basically 64 cross 8. So any memories that you see, it would be kind of say 64 cross 8. okay, or 128 cross 4, okay, say 32 into 24. So something like this. So what is the meaning of this configuration? Okay, they are all kind of depicting your number of bits under the word lines. Okay, so it shows how many values that the memory can store it. So this is kind of bigger, and this kind of smaller, and but this kind of much bigger, and this kind of much bigger. Okay, now let's these are all the small standard cells that we talk about. So say for example, this is your NOR gate. Let me bring up the schematic. Okay, now so the circuit's gonna be, okay, now you see this. So this is something that NOR gate. It is going to a full adder. You guys can see it, I believe, right? No. So FA, it's basically so mux. Sorry, there's a full adder, and so if you look at right, your design would be say something like this. Okay, you'll have lot of paths, probably combination circuits. So whatever that we are drawing in our the while learning, say for example, now you're looking at this counter, right? Say this counter is having how many cells? Only one between here, the two flops. But in industry, you will have at least minimum of say 10, or it can be minimum, can be anything, or average. Okay, I have seen 30 plus cells. Okay, average there would be a 30 plus cells. Don't think that okay, just one or two. There would be a 30 plus cells in the designs that you will see in the industry. Okay, so you see here there is a NAND gate, and there is a NAND gate here, NOR gate, and these are all something like kind of OAI. There is a cell called OAI on or and invert. Okay, so this is how your design schematic would look like. Okay, now if you guys remember the ASIC flow that I covered in the intro class. So what did we cover? So the first thing is basically a RTL design. Okay, RTL design, then synthesis. Okay, and then your DFT comes into picture, and then your PD, and then finally your tape out. Okay, now RTL design is going to be more of a programming style. It's like kind of like how you write C programming, right? C plus plus and etc. So RTL design would be written in the form of HTL. So people use either Verilog, okay, or system Verilog, SV. Okay, now synthesis is what actually converts it into the gates format. So it's kind of program. Now when you do synthesis, that particular the programming style, whatever that you have written, is converted in the form of say basically gates, and how they are supposed to talk to each other. Say you have another flop here, so now this flop is talking, this thing is goes here. So assume there is another flop. So from here it goes to say another gate. So this is how you actually come up with the circuit. Okay. Now this whole process, you converting the Verilog HDL, okay, into a gate level netlist is called synthesis. Okay. Basically it is written kind of in a program. Now this is converted into the circuit. I probably say gate level circuit. Now we also talked about something called the DFT. So they add that, convert all the regular flops to SDFF, scannable flops, and we also add some extra logic for to make the chip testable, and then PD, which you are going to learn, and then once you're done with PD, then you will have finally the tape out. Okay, now this is the circuit that you would be actually working on. Okay, now that circuit, you can see it in the tool, something like this. Okay, and you are not the designer, for your information. Since you are a PD engineer, the circuit is given to you. Now you have to, what is your role here? Your role is take this circuit, this design. Okay, now you would be given an area like this. So you see here this square, this is basically your area, the chip area, or probably your block area. Say this is your block area that is given to you. Now you have to implement the design in the given area. Okay, that is what you are going to do. Now during this whole process, you will follow different steps. Now that you will learn it probably in a couple of weeks later. Now coming back to the designs, so you have seen under gate, OR gate, and all of that, right? The PD guys will see everything as a kind of this kind of dabbas only. Okay, if you see here, what is this? This SDFF. You have all the kind of flops converted as a SDFF. Now you see here mux, and this is also mux inverter. So the thing here is, so any AND gate and OR gate, right? So we talked about logic gates till now, right? Now, so we till now discussed in terms of gate levels, like how you implement the design and etc. Now you need to understand, or probably it is a time to understand how these gates are manufactured, how they are manufactured. That is, if you try to understand that, then you will, if you really wanted to understand that, then you need to go and learn something called what is the technology that we are going to use to manufacture this. So we currently have something called CMOS, and if you look at the latest thing, there is something called FinFET. Okay, and there is one more thing, the latest 3 nanometer and etc. and all of that is going to be known as, say, gate all around fit, GAA fit. Okay, so if you ask me, learning about CMOS and learning about FinFET is good enough for you to get into industry. Not a big deal at all. Now, so CMOS is what we are going to learn first. Okay, FinFET is kind of little advanced that we will learn probably towards the end of the batch. So CMOS is what you're going to learn, and for this, you should know how a MOSFET operates. Okay, how a MOSFET operates. Now, how do you design an AND gate using MOSFETs or CMOS? Okay, so that we will see it now. Any kind of AND gate, OR gate, and everything. The height of the cells, they're all kind of same. So all these we will discuss in today and as well as in the next class. So you see this. Cells have different sizes. So height is same, but they can vary in terms of width. You see this? See, you have this cell. So all the cells, if you look at in terms of height, they are all kind of similar. So why we have all this? What is the advantage? And all these we will be learning. Now, what is your meaning? What is your role? So I want you to understand. So you have given a gate level circuit. Okay, now that gate level is actually implemented in a given area. Now assuming Say this is your land that you wanted to construct a home. Okay, so this is your land. Now you are going to construct a home. Say, for example, you need, kitchen, and you would be planning your bedroom, and then you will have your hall, study room, and etc. Now this is the place where you have all your entries and exits. Okay, your block would be talking to outside, correct? Entry and exits. That's nothing but the door area, and etc. So that is the overall thing that you would be doing. So you will be implementing a given design in a given area. That is what you are going to learn, or you would be doing in the industry. But now to do that, you need to know a lot of concepts, and you need to practice a lot that you will be learning. Okay, now I don't want to spend too much time on this at this point of time. You might not understand anything. uh, we will move on to our regular topic, but before that I think I missed one topic, that is something called setup time and hold time. Did we discuss? Can someone confirm? I guess no, but setup time, hold time, did we discuss? Okay, all right, great. Thanks for the confirmation. Let's go ahead. Now simple, right? uh, Say you are, this is your airport. Okay, now, so your flight. Now say you are traveling to airport. Now what is that they say? Say your flight is at say 12 o'clock. Now what they say? Your flight departure is at 12 o'clock. Now what is that they say in the instructions? So basically you have to reach the airport at least 45 minutes before. I'm not sure. This was the case probably 10 years. Now I'm not sure if there is any improvement or they have added more time. So assume say 45 minutes to 1 hour time. So let's take 1 hour. So you have to reach airport 1 hour before. You need to collect your boarding pass, and then you have to go for check-ins, luggage, baggage check-ins and everything. So that means, though your flight is at 12 p.m., but what is that they are telling you? You have to be inside by before 1 hour. Okay. Now, so this is exactly what we call it setup time. This is exactly what we call it setup time. So basically, now say the setup time meaning before the clock arrival, the data. So this is your data, and say this is your clock, and this is your POSIX triggered flow. Okay. Now before the clock arrival, the data has to be stable for some time, so they cannot change. So you cannot have change. You cannot have logic change 0 to 1, or it is kind of switching. So the data has to be stable before the clock arrival. Say this is something that we call it T setup. Okay. Now can you relate the same thing with your airport time? Because your flight is at say 12 p.m., but you have to be there 1 hour before. Now this 1 hour is nothing but your, say, you can call it a kind of setup time. Okay. Now, so the same airport, so your flight is landing, the same flight. Basically it's not the same flight, different flight. So assume you have a landing say at 4 p.m. Okay. Now you would be, so this is your again airport. Right now you would be, what time you would be coming out collecting your baggage? You would at least spend minimum 30 minutes, because they have to bring your baggage, after you getting down, and they have, you would be reaching airport through a bus, and then you have to wait for your luggages to collect, right? and then you will come out. Now, what is this meaning? After your flight landed, you cannot come out immediately. There is some time again that you have to give there, right? So that is nothing but your data has to be stable again after your clock arrival. The data has to be stable after clock arrival. So this is something that we call it T hold. It's basically T meaning it's basically setup time and hold time. Okay. Now, is this a very strict requirement? The answer is yes. You would definitely need to meet all your setup time and hold time requirements, and the whole thing is basically comes under a topic called STA, static timing analysis, that industry people would do. Okay. Now, at your textbook level, this is how it would be. If you go and take any kind of your design, the digital textbooks, this is how it would be. But we do it the same, so it's kind of setup time. Now we do something called setup analysis. Okay, setup analysis or setup check. Okay, and then there is something in a way hold check and hold analysis. Okay, so this is something that we do extensively on all our circuits. So if you guys remember when you say PD taping out, so STA is throw out your PD. So when someone is saying a PD engineer, they definitely need to learn STA. Without STA, you cannot be a PD engineer. Okay, so it's nothing but you doing a timing analysis whether the data is reaching on time or not, etc. Okay, so we will learn more on that, but probably just to understand basic concepts, so you guys can go back and revise your setup time and hold time basics. And if you wanted to learn more of it, okay, you can go and look at how do we do setup analysis and how do we do hold analysis. That would give you basically the information. Okay. Okay, I think that's all I wanted to cover on the whole digital part. Any questions before we move on to the CMOS part?